In this video, we're talking about arrays. Previously, we've used variables such as x equals 5 to store a single piece of data, this being the number 5 in this example. Now we extend this to arrays. In arrays, we store multiple pieces of data under a single name, such as x. This allows us to carry around many bits of information into various programs by using just one name instead of many names, such as x1 equals 6, x2 equals 3. Instead, we can put them all under a single name, such as x. So to demonstrate this, the best way is to simply show you. So for example, previously we've used a single variable, which I will call num, short for number. We've previously used it just to store a single value, such as 10. Instead now, we're going to be using arrays to store multiple pieces of data. Some of the most simple arrays are vectors. A row vector, as I will construct here, contains a single row with multiple columns of data. To construct it, we use the open square brackets, followed by pieces of data that we want to include. We separate data by commas, and we close the array with a square closed bracket. We can put a semicolon on the end to suppress output, but we will leave it off so we can print to the command line to see what this array looks like. The second type of array I want to mention is a column vector. This is of a similar construction to the row vector, except instead of commas, we separate data by semicolons. By using a semicolon, we'll soon see that it creates a new row in an array, forcing this vector to take the form of a column. If I just save this now under my directory, I'll call this arrays. If I must save this again because I left off the M. Sometimes your MATLAB installation, especially if it's a Windows installation, it usually takes care of this for you, but this time I forgot to put the M. So if we execute this program, we see now the number we had before is just a single number, and if we look here in our workspace, we see we have num that has the value 10, and if we put our mouse over it, double click on it, we can see that it comes up here as a 1 by 1 double, and as a 1 by 1 array with the number 10. If we just close this now, row vec we see takes the form of a row, as I said before, and the col vec takes the form of a column. If we look at both of these in the workspace, if we double click on them, you see it's 1 by 5, so 1 row by 5 columns. Likewise, column vector is 1 column with 5 rows. Okay. Now, these are special, simple cases of arrays. The most general type of array that we're going to come across is simply called a matrix, and that's where MATLAB gets its name, MATLAB being short for Matrix Laboratory. So a matrix is any size array. Most people call it M by N, that is M rows with N columns. In the simple case of a vector, one of those dimensions, either the rows or the columns, reduces to 1, and the other one is the dominant dimension, where we see we get multiple columns in a row vector, or we get multiple rows in a column vector. So let's just construct a general matrix. If I just plug in some numbers, notice I've separated these elements by a comma here. This means a comma is adding another column to the array. By inserting a semicolon here inside the array, I'm forcing the array to move to a new row. So this data here is going to be the first row of my array called matrix. The second row is going to contain, let's say, 15, 3, 6, 10. The third row, should I say, let's say 8, 3, 1, and 12. And I close the array as I have done before with a closed square bracket. If I save this now and run it, we see the same output we had before, a single number, which is a 1 by 1 array. That's the simplest kind of array we can have, a 1 by 1 array. We have a row vector, which is a 1 by 5 array in this case. The column vector is 5 by 1. And this matrix is a general array, and if we look at the dimensions, it's 3 rows with 4 columns. So we would say it's a 3 by 4 array called matrix. We can look at this in the workspace. If we double click on it, we see, as we said, 1, 2, 3 rows, 1, 2, 3, 4 columns, and this is the data contained within it. This view for the variable editor looks a lot like Microsoft Excel. So likewise, you can actually click on this and change it. So I'm going to make that 6, and I'm going to make this -5. So now if I go to the command line and enter matrix, I'm just going to close this to get some screen space back. We see now matrix has changed this 3 to a 6 and the 1 to a -5. So that this is how we construct arrays, and we can see the dimensions that they take, going from a simple 1 by 1 number up to a general m by n array. Now, to more efficiently access data instead of using the workspace editor, we can simply index or address elements. When I say elements, I mean single bits of data in an array. We can address them by referring to their location in the array. There are 2 ways of doing this. The most simple way, which I prefer, is to use what we call matrix indexing. So to access a single piece of data, we simply use the name of the array. In this case, this one is called matrix. To access, let's say, this element here, we use the name matrix. We open a parentheses. Now, to access a particular element, we put the row number, followed by a comma, followed by the column number. So this is kind of like what you may have done in some coordinate geometry classes before in mathematics. So we're referring to the exact row and column of a element in an array. So for this number 10 here, it would be row 1, 2, separated by a comma, and it would be column 1, 2, 3, 4. If I close the parentheses, we see it is as we expected. Likewise, let's try number 8. To get that piece of data, we use the same matrix indexing. We use row 1, 2, 3, followed by a comma, and this is column 1. So this is how we retrieve single pieces of information from an array. With this retrieval, we can also do operations. So we can go matrix 3, matrix, row 3, column 1, which is the number 8. We can do an operation on that. So we can multiply it by 4. We can put some parentheses around it. Remember, the more parentheses define the order of operations. So if you're unsure of the order of operations in a line of code, such as addition with multiplication and division and subtraction, it's always useful to use parentheses. So we can take a number, take 15, and we'll have some result. So this is how we use the data to do mathematical operations. Likewise, we can change a single piece of an array, just as we did before in the variable editor. We can change it by referring to that address in the array, as we did before, but instead we use the assignment operator, which is given by the equal sign. We can make it perhaps negative 54. And as we see now, this element's been changed to negative 54. So we can now retrieve data and we can edit data in an array. Some other useful things we can do with arrays is that we can measure them per se. By measure, I mean one operation we can do is we can use this function called size. Size, if I use the array called matrix, that will give us the dimensions, where the row comes first, followed by the column size. As we said before, 3 rows by 4 columns. Additionally, we can use a function called length. Length gives the largest dimension of an array. Personally, I think the length function is more useful when we're dealing with vectors, because if we use length with matrix, we can see there's 2 important dimensions at work. There's the rows and the columns. In this case, the largest is the columns. For example, with the row vector, if we use length row vector, we see there's 5 elements in the row vector as we expected. This is useful for us to find the amount of elements inside a vector. Another way of measuring an array is by using the max function or the min function. We see here we've typed max, which is a MATLAB function, and it's suggested that we can use a as a input to this function. When they say a, it just means any general array. So we put in max matrix, and what they've done here is they've summed up the columns. I should say they haven't summed up the columns. They've found the maximum element in each of those columns. Whereas if we apply max to col_vec, it sees the maximum number as 29. Likewise, we can use the min function on col_vec, and that will get the minimum element. So that is the smallest number inside the array. Another useful thing we can do is with larger arrays, such as matrix, we can take sections of this array for us to do other operations with. So let's say we can just have a vector called test. So let's just call it test, and we're going to assign the value to test to be a section of this array matrix. To do this, we should pick a section. So let's say we want test to have the entire second row of matrix. To do this, we need to index or address to the array called matrix. We do that by using the name, and we can use a special symbol, the colon, which indicates that we want to take the entire section of this particular dimension. So if we want the second row, we use 2 to indicate row number 2, and we use the colon to indicate that we want every element in every column that is in row number 2. If we execute this now, we see we've pulled out row number 2 from matrix and assigned it to some variable that we call test. This is useful in breaking up arrays. Finally, we can use a special operation in MATLAB to generate a vector of spaced points. Let's call a vector A. We can generate it, let's say, to go from 0, up to 25. We see now A has been produced as a row vector with one row with columns 1 through to 26. So it starts from 0 up to 25. The spacing between each element is 1. We can manually change this spacing to be, say, 2. Now we have a row vector with spacing of 2, 0, 2, 4, 6, 8, etc. Notice I used 25 as the final value in this vector generation operation. But notice the final value here is 24. Because I used 2 as the integer separation between each of the elements, it's going to go from 0 up in even steps of 2 up to 24. Since 25 was the limit, we're not allowed to go to 26, and so the vector is finished here.